in this lesson we're going to take a look at rotational kinetic energy and momentum. So remember, we have two things. Rotational kinetic energy is given by 1/2 I omega squared, but we also know that angular momentum, L, is equal to I omega, and the same rules that apply to linear momentum apply to rotational momentum. So momentum is conserved, but also net torque times time equals change in angular momentum. So let's say we go back to the problem where we had an object on top of this ramp. We're going to let it roll without slipping down the incline. It starts at some height h. What I want to know, if this is, say, let's go with 0.5 meters here. This is a 30-degree angle, which makes this a 1 meter long ramp. I want to know how long does it take this thing to get to the bottom, so time. I want to know how fast is it going at the bottom, so final velocity. And I also want to know the net torque that is acting on this thing. Okay? To solve this problem, I'm going to use energy, and then I'm going to use momentum to figure all this stuff out. You could just use Newton's laws, and if we have time, I might look at that. So let's start with our energy equation. We know that the potential energy at the top is equal to the kinetic energy at the bottom because no energy is lost. So that means mgh equals 1/2 mv squared plus 1/2 I omega squared. And let's say this is a cylinder, a hollow cylinder. And so when we have a hollow cylinder, the moment of inertia is given by 1/2 mr squared. And we'll go ahead and say the radius of that thing is 0.05 meters. Okay, so we've got mgh equals 1/2 mv squared plus 1/2 I omega squared. We're going to make our substitutions. So mgh equals 1/2 mv squared plus 1/2 I, which is 1/2 mr squared, times omega squared. And then we make our substitution for omega. So mgh equals 1/2 mv squared plus half of half is a quarter, m, and r squared times, and instead of omega, we're going to use v squared over r squared. R squareds are gone, and m is also in every term, so it's gone. So gh equals 1/2 v squared plus quarter v squared, or gh equals 3 quarters v squared, or v is equal to the square root of 4/3 times gh. So I've figured out what v is. I know h, it's 0.5, g is 9.8. I could find a number for v. So v is equal to 4 divided by 3 times gh square root. I also want to get the time it takes for this thing to get to the bottom. So for that, I've got two equations that involve time. 1/2 at squared plus v naught t equals delta x, or v equals v naught plus at. Both of those involve acceleration. So I need the acceleration. So I'm going to start with that. So v squared equals v naught squared plus twice the acceleration times the displacement. I know the final velocity, and squared is 4/3 times gh equals, and the initial velocity is 0, plus 2 times, and I said the length of that ramp was 1, and so my acceleration is a. So 4/3 gh equals 0 plus 2, 1 times a, and so a is equal to, divide both sides by 2, 2/3 gh. Okay, so there's the acceleration, which actually I can use to find time because v equals v naught plus at. And so there's my final velocity, square root of 4/3 gh equals 0 plus, there's my acceleration, 2/3 of gh times time. Divide both sides, and I get time is equal to square root of 4/3 gh divided by 2/3 gh. And you can do that math, you can figure out what that time is. Now the last thing to find is actually the net torque. And there's a couple ways you could do this. You could say net torque equals I alpha. Net torque equals I alpha. And you could find the moment of inertia of that thing, which we have, 1/2 mr squared. The angular acceleration, which we could get because we know the linear acceleration. All we have to do is divide that by r. Or we could use this equation, which says the net torque is equal to the change in momentum divided by time. And since we know its final velocity, we could also get its final angular velocity. So there's a lot of different ways to solve this. I'm going to use this one real quick. So net torque is equal to the change in angular momentum divided by time, or the change in time. Well, there's my time, whatever this is, t. Here is change in angular momentum. Well, it went from 0 to having some. So v, we know our final velocity is right here. To get that, v equals omega r. So if I divide v by r, I get omega. So all I have to do is take I omega divided by time to get my net torque. So I would have 1/2 mr squared times omega, but remember omega is just v over r, and then I would divide that by time. So I would have the net torque is actually equal to 1/2 of mrv over t. Okay? So there you can use momentum to get your net torque, or you could use Newton's second law for angular motion and your angular acceleration to get your torque.